Let us talk about scale-dependent complexity for a bit. So this is a topic that really confuses the hell out of people, even professionals. And the problem here is that some people say that, hey, this thing is very complex because it's a complex system, and other people say that no, we can actually do things in the system that are quite simple and so forth. And so people can call the same system simple or complex or complicated, whatnot, without realizing that they might be actually talking about different aspects of the system. And one way to view these aspects of the system complexity is talking about scale. And this is going to be a bit uh, difficult, perhaps, but let's try to hold on. So the first thing to understand is that we could understand systems in with three concepts. So first of all, systems have a state. So if I'm a system, I'm now giving a lecture or I'm talking. Systems have a scope. So um, my scope could be my body. And if I expand the scope of this system, my scope could be my family system or my neighborhood, my community, my society, and so forth. And if we expand the scope, new things start appearing, and that's something we call emergence. And then finally, we have this thing called resolution. So you can observe me or if you imagine this screen that you can have different types of resolution in it. So basically, you can, at this resolution, you can see me talking. At lower resolution, you might only see the shape of me. And if you would have super high resolution, you could include in this description of me, you could include all the skin pores and so forth. And if we continue with this analogy of a camera image, imagine that there is a top-mounted camera in this heavy metal concert. And there are people who are attending the concert, and you have the opportunity to watch the concert on your laptop and change the resolution that you watch the concert through. So when you change the resolution, the concert, some things become blurred until you only see the largest scale, the biggest structures, and the most defining features of the whole thing. So a state in this sense could be the position of people around this um, area, or whether their music is playing, and so forth. Scope is what you see. And what we are going to be doing is we keep the scope constant. So we only we keep the screen, everything in the screen that so this is our system, what we see. We won't be expanding the perspective, or we won't be narrowing it down. We will see the same thing constantly. And now, if you imagine different parts of this concert, you can consider that you can see different types of detail. So if we have on the vertical axis, we have the system's complexity, or the number of behaviors that the system can do. So how many things can the system perform? And on the horizontal axis, we have the scale. which is in this case equivalent to inverse resolution. And I really, really suggest having a look at the description in this paper that's in the bottom of the screen, and because it introduces the basics of this perhaps in a more analytical way than I can at the moment. So let's think about the progression of this concert. So first, people are sort of waiting for the band to start. So they are in the audience area, and they're just doing their thing. They're just walking around. One person is perhaps moving to another part of the spot, and but someone else is soon replaces them, and so forth. So in this case, if we have a large resolution, we can see many things. But as we blur the resolution and the concert hasn't started yet, we're just going to eventually see an indistinct blur, or across all these resolution settings, we see basically the same thing. So there's a bunch of people sitting around, and they're like pretty much the same, and sort of equivalent to each other. But as we change the resolution, it's the same thing that we see all the time until we see nothing in the end when the resolution is blurred enough. But next, think of the situation where the band comes on stage and starts playing, and now things start happening. So we have on the outskirts of the audience area, you might have people sipping drinks. In the front of the audience area, people might be shaking their fists, and somewhere in the middle, you might see these patterns like mosh pits and stuff like that form, which are kind of observable even at very large or very poor resolution settings. So in this sense, you have sort of different things happening. If you include a lot of resolution, you can see all the individual finger movements and all of this that people are doing, and how their mouths are moving, and the like micro movements that they're doing. But most of this is really unimportant for describing the situation where the band is playing. On the other hand, in the middle setting, middle resolution setting, you see sort of something different. So you can focus on those mosh pits and different types of behaviors that people do on the different parts of this audience area. And eventually, when you blur the system enough, you start seeing basically nothing. But now when we move to the final stage of the concert, where the band says, thank you, good night, let's go out, and people start looking for their way out. And now what everyone is doing is basically the same thing. So everyone is doing the same thing. They're moving. Let's say there's an exit to the left of this area, and everyone is moving toward that exit. And in this case, the movement of people, we can call it coherent. So in this case, when you have the large resolution picture and you start putting the resolution to a lower and lower setting, you will basically see the same thing. People move, a mass of stuff, in this case, people moving to a direction. So everyone is doing the same thing. And increasing the resolution doesn't really give you much new information in this phase of the concert. And what we can sort of derive, and this is from a book that I will show. It's called Making Things Work. So I've left out many details, but just to summarize, we can say that summarize the implications of this sort of an inspection. So this reads that an analytical approach should focus on distinguishing those processes that are large scale, so low resolution, and therefore can be performed efficiently, from those processes that are highly complex, requiring individual specialization or even teams to perform. So when we're doing a real-life analysis of what should we do with a complex system or with a problem that we have, we should separate the large scale and the complex from each other. And we continue that when large-scale tasks are identified, then we can adopt this traditional approach where we centralize authority, we institute standards, we try to make everything uniform so that they can be done efficiently and like optimize the system, so it works more smoothly, and we get these sort of economies of scale and so forth. But for the complex task, we can't do this, and we shouldn't do this because otherwise we'll be in trouble. Instead, when complex tasks are identified, then we should adopt this evolutionary approach to distributing decision, action, and authority, setting these functional goals for what should we do, directions for improvement instead of these grand outcomes. So setting a direction is very important here. Supporting individual initiatives so that people can use their local knowledge to start making these micro-scale improvements, and instituting redundancy. So when something fails, it doesn't bring the whole system down with it. Forming cooperative teams, because teams can really work on a much more difficult set of problems than individuals can, and creating rules that promote competition with performance feedback. And this is discussed in another video of this series, more in depth. But to summarize, it is more difficult to address this complex system because there is no universal organizational structure that will work for all cases. So we can't just do the same thing for everyone. But what we can do is we can try to separate these things from the more straightforward situation. And but we don't need this sort of an analysis if we use this an evolutionary approach where we have a lot of variety, and then there is a selection process that selects the best experiments or probes or trials based on what we have going on. And so this is the book. You can find it, the PDF is for free in this link. So just to give a summary of this, so we separate the complex from the large scale. But there's also another thing, another way to do this separation. And there are two references on the bottom that I will describe now. So this is the CARMA framework, basically, overlaid by Max Boisseau and Bill McKelvey on this on a similar vertical axis as what we have discussed during this talk. So what we have in this sense is we have three areas. The bottom one is called ordered, in which case we do this, we look at what information is available, and then we either analyze data, or we look at, oh, this problem goes into this category, and then we respond appropriately. So this is seems like something that could be done very large scale also. And then in the middle, we have this space called complex. So we probe with experiments, and we try things out, and we look at what happens, and then we respond appropriately, sort of like a martial artist or dancer responding to the movements of the other person. And on the top, they call this chaotic. It could also be stochastic or random, but in this case, you just do something because it's often a crisis situation. So you need to do something to stabilize the system. Look at okay, so are we finding these things that we can actually start working with, or do we need to do more stabilization actions, and then we perform appropriately. And these two things have not been, to my knowledge, brought together, but you can use your imagination to think how these things could or could not fit together. So the right-hand side and the left-hand side of the screen. There's also this dynamic that goes into Cynefin, which is that you have these complex situations where you do these probes or trials, and you find out, hey, this thing works. And when I do this thing with these parameters or these background assumptions, then it produces a predictable result. And then the thing becomes an ordered problem, and then something changes eventually. And then it stops working, in which case you need to go back to trying stuff out and finding out what works. And in this sense, there's this dynamic of exploring in the complex, and then exploiting when you bring it to the more ordered domain, and then back to exploring, and so forth. And so this is what I wanted to say for now, and I hope and this will spark some discussion on the similarities or the differences between these two approaches of breaking down the world.